Next.js 16.2 includes over 200 bug fixes for the TurboPack build engine, alongside multiple improvements to developer tools and agent integrations. But beneath those standard workflow upgrades lies a solution to a much deeper architectural problem: the high latency previously required to process React server components, or RSCs, the architecture that renders components to static HTML on the server before sending them to the client. When diagnosing this latency, engineers found that the bottleneck was not the raw byte size of the RSC payloads themselves, nor was it bandwidth limitations on the network. The delay was hard-coded into the execution mechanics of the V8 JavaScript engine, the open-source engine that powers Node.js, specifically in how it handled native JSON parsing callbacks. This architectural model of the Next.js runtime environment shows the immediate result of bypassing those mechanics. The engine layer achieves a 350% increase in deserialization speed, translating directly to a 60% faster rendering pipeline. We are going to deconstruct exactly how Next.js engineers bypassed the V8 execution boundary to unlock these speed gains, and how new network route fetching heuristics are reshaping the framework's architecture. The most significant performance leaps in modern web architecture no longer come from higher-level API tweaks. They come from confronting the bedrock limitations of language runtimes. This diagram of the V8 engine architecture tracks an incoming raw JSON RSC payload as it enters the C++ side. Earlier versions of Next.js processed this payload using the standard JSON.parse method, passing a reviver callback to transform the data. The JSON pairs operation executes entirely within V8's fast, compiled C++ environment. The inefficiency stems entirely from the reviver callback. To execute this logic, the engine halts C++ execution, crossing the internal boundary back into the JavaScript runtime. This boundary crossing occurs for every single key-value pair within the JSON object. In production, a single component tree contains thousands of individual nodes, forcing the engine to jump back and forth across the boundary thousands of times in milliseconds. The raw performance penalty is severe. Adding even a trivial, no-operation reviver callback degrades the efficiency of JSON parse by a factor of 4. The framework's rendering pipeline was choked by the micro-latency of continuous context switching across the engine's internal execution boundary. Looking at this updated engine model, we see the new architectural approach in Next.js 16.2. Deserialization is split into a strict two-step process to maintain runtime isolation. Step 1 executes a bulk plain JSON.parse operation without any reviver function attached. This allows the parsing operation to utilize the unhindered C++ execution path from start to finish. In Step 2, the engine parses the fully parsed object across the boundary exactly once, performing a recursive walk through the object entirely in pure JavaScript. Isolating this recursive walk within the JavaScript runtime eliminates the per-node boundary crossing overhead that previously bottlenecked the operation. This two-step isolation also unlocks a secondary optimization. The engine can now safely short-circuit plain strings that do not require transformation, skipping unnecessary processing entirely. Translating these theoretical mechanics into real-world application benchmarks reveals the practical impact. This data comparison chart displays server render times. For a server component rendering a table of 1,000 items, the render time drops from 19 down to 15 milliseconds. A Payzod CMS homepage sees its render time reduced from 43 down to 32 milliseconds. The most significant improvement occurs in data-heavy, rich text CMS environments, which accelerate from 52 milliseconds to 33 milliseconds, a 60% increase in rendering speed. Intelligently restructuring code to respect language runtime constraints yields far greater rendering acceleration than optimizing the React component tree itself. Moving up the stack from the engine execution layer, we reach the network layer, where Next.js 16.2 alters its route fetching heuristics. This visual contrasts two network behaviors on a hierarchical route tree, starting with the Next.js 16 default, granular per-segment prefetching. The primary advantage is high cache efficiency. Shared layout payloads between sibling routes are fetched exactly once and heavily deduplicated. The drawback to this strict deduplication is a massive spike in concurrent network request volume. On high-latency connections, this creates severe network waterfalls, where the browser must wait for sequential requests to finish before proceeding. To solve this, Next.js 16.2 introduces the experimental .prefetchInlining configuration flag. Inlining changes the mechanical behavior of the network request, bundling all the required segment data for a specific route into a single, unified HTTP response. The framework intentionally sacrifices strict cache deduplication to eliminate the round-trip latency of multiple sequential requests. With this flag enabled, shared layout data is duplicated across payloads. This is not a permanent binary choice, but a stepping stone toward a future, size-based caching heuristic that will handle small and large segments dynamically. Optimal network architecture is rarely about absolute efficiency. It requires a deliberate rebalancing of trade-offs, prioritizing reduced connection overhead over pure payload deduplication. Dropping from the network layer down to the final stage of the lifecycle, we reach browser hydration, the process where React attaches event listeners to server-rendered HTML and client-side error recovery. This technical mock-up of the Next.js development error overlay specifically highlights the new hydration diff indicator paired with the new unstable retry function. When a render mismatch occurs, the hydration diff indicator explicitly isolates and labels which DOM nodes originated from the V8 render on the server and which were generated by the browser render on the client. Beyond visual debugging, production runtime resilience has also been upgraded to better handle failures during data fetching or RSC generation. Previously, developers relied on the reset prop in their error boundaries. This cleared the local UI error state, but could not recover failed server data. Next.js 16.2 introduces the unstable retry method, making it available directly to error boundary components. Because it is transition-aware, unstable retry triggers a router.refresh nested within a React start transition. Error handling has evolved from a blunt, localized state wipe into a precise, full-stack operation that orchestrates fresh data fetching without breaking the user's UI transition. This diagram of the three-tier model illustrates a single request flowing seamlessly through the optimized 16.2 stack, from the server, through the network, and to the client. The 60% rendering speed increase is a direct result of respecting lower-level V8 runtime constraints, rather than attempting higher-level API patches. This shift in route fetching heuristics proves that maintaining high performance requires continuously reevaluating assumptions about caching versus connection volume, and the maturity of a framework is defined by its ability to push error recovery deep into the component and transition lifecycles. Mastering Next.js 16.2 demands an understanding of the full stack, from the network topologies of the browser all the way down to the execution boundaries of the JavaScript engine itself.